and this is part of general set of results I've done recent years about IPS and algebraic proof, strong algebraic proof system. This, in some sense, summarize some of the stream of results related to one approach to prove lower bounds on IPS and strong algebraic proofs. So the motivation is this: we want to study lower bounds against strong proof systems. Strong here, as I said, is going to be IPS, it's strong algebraic proof system. It turns out that this actually simulates almost all concrete known proof system like extended Frege and Frege. So this is a good starting point. Try to prove some lower bounds, maybe on fragments or on IPS. Now, we want to focus on a specific method within IPS lower bound, and this is the functional lower bound method. That was arguably the most or the major approach to prove lower bounds in this on IPS, and this is based on a reduction to a circuit complexity. What we're going to show is we expand the range of applications to all symmetric instances, and I'm going to show Newton's degree lower bounds for all symmetric instances over different. We're going to extend what was known to different kind of hard instances that are slightly different than subset sum, and that's why they will also work over finite fields. And then we do some quite heavy technical work on improving the constant depth IPS lower bound result. We're going to show, or in this work, we show something that is stronger than was known before, based on some improvement on individual degrees in the refutations. Now, at the end, we're going to show some limitation on this technique. So this technique, the functional lower bound, which I will describe, has limitation in the sense that it's not going to work, at least solely, it's not going to solve the big problem of constant depth propositional proofs with counting gates. And we could show this formally. It's not extremely complicated to show this. Now, it doesn't mean that other results related to IPS or even some results inspired by functional lower bound would not work for these kind of major open problems. It's just that specifically this functional lower bound alone would not work, and I'm going to show why. Right, so here is most of the facts you need to know about the proof system. So we have algebraic proofs. People have discussed this already. We have the set of polynomial equations, Fi, that are unsatisfiable. The set is unsatisfiable over the Boolean over 0, 1, right? And Newton's refutation is the following. Refutation is just this formal sum of the product of the axioms Fi and then the product of the Boolean axioms. And they equal 1 as a polynomial identity, right? So this is the usual Newtonian result. And here, let's extend the complexity measure to understand what is IPS. So we have this spectrum from proof system is Newtonian result, complexity measure, the maximal degree of the summand Gi times Fi, or a summand Hj times a Boolean axiom, right? That's the degree. Now, if I'm speaking about size measure for Newtonian, that is going to be the number of distinct monomials in those summands, right? This is monomial size, and this is Newtonian. Now, if I go up and I consider circuit size, algebraic circuit size of the summands, Gi's times Fi's, or the H times the axioms, what I get is IPS. So that's it. It's basically Newton's written as algebraic circuit.
Do you have any restrictions on the verification procedure?
Yes, it's not a Cook record proof system. It's like it's probabilistically verified. But we are interested in lower bound, so this is even worse. So it doesn't matter. So now, yes, and this is another model for size, which is interesting. It's what I call the placeholder circuit size, what we call, and it is the following. I just consider the size of GI and HI. I ignore the axiom Fi. So Fi, the axiom can be very big. I want to prove something very big, but because of the way it is defined, I can just consider the size of GI, and even there might be interesting to show that GI might be small, although the axioms are big. It's not completely natural in Frege, but it is natural in this setting. And indeed, this was exploited in original work. I'll discuss this. Now, what is this? This is just the same, but I want to consider C circuit size, circuit class C. So I write the IPS from a specific class C, right?
So you have a lin. What's the lin mean?
Oh, I said lin. Yeah, lin means that it's linear. So it means that the axioms comes with do not power themselves. Comes with power 1. It's just technicality, not extremely important. Some small limitation. It doesn't matter for when C is any general algebraic circuit. But when the circuit class is somewhat restricted, it might be important if you can power the axioms. Forget about this. Now, what is the functional overbound? The functional overbound is the following: very simple reduction, which in some sense is reminiscent of the feasible interpolation. It's a reduction between proof size to circuit size. And here it's even simpler. So consider a refutation of a single. It's important that it is a single axiom, fx equals 0, unsatisfiable over 0, 1. And this is the refutation, right? Now this implies that G times F equal 1 over the Boolean cube. So in order to prove a lower bound, now notice that this is a polynomial. This is a polynomial identity, and this is a functional identity. This is a just equal 1 as a function of the Boolean cube. There's a family of polynomials that will have this property, not 1. So we just divide, and we have G equals 1 over F of the Boolean cube. So we reduce the problem of proving for a single 0, 1 unsatisfiable axiom F equals 0, lower bound on this, on size of refutation or even degree, to the goal of lower bounding G polynomials that compute G, which is this function over the Boolean cube alone. Yeah, that's any question. Results and technique. Well, we have this paper. It's going to be out soon, hopefully in a couple of days. It has a lot of results. I'm going just to list the result and say something about ideas. Right, so symmetric instances are hard for Lutz-Lenses, all of them. So if fx minus b is symmetric, symmetric means fully symmetric, namely renaming the variables keeps the polynomial the same, then, and it's unsatisfiable in this case, then for b sufficient b, it will be unsatisfiable, then it is hard for Lutz-Lenses degree, in the sense that even if this fx has degree d, to get the lower bound, you need the degree n plus 1 to get the refuting, right? So even if you have the start from constant degree or logarithmic degree of the symmetric polynomial, you have to go up quite to linear degree to get the lower bound, to get the refutation.
Or
So,
It will be even harder if it is satisfiable.
That's correct.
The result is so you won't have to specify such things.
So this theorem is for every F and every V.
Every F, well, it's the same. If F is symmetric, then F minus B is symmetric.
B is a constant.
B is a constant, sorry. So it's the same. If, as Sasha said, we don't need to say it's unsatisfiable. Any refutation of this will be of high degree. Now, what is the, this generalizes my work with Forbes, Shpilka, and Wigderson, right? So what we considered there was the subset sum. So it's just the sum of variables, which is symmetric polynomial of degree 1. So we did it for every degree. The idea, I had it here, but I wanted to talk about something more interesting than I deleted just now. The idea is, well, product of two non-constant elementary symmetric polynomials whose sum of degrees is at most n. So if you have two elementary symmetric polynomials, you multiply them. If their sum of degrees is doesn't go beyond n, then you must have a non-zero monomial there, which is different than 1. So if it equals 1, the refutation must equal 1. It cannot happen, because if the refutation equals 1, there must be all the monomials must be 0 except the single monomial 1. So that's kind of a nice computation. Now let's look at this. This is new quantitatively. This is based on vector invariant polynomials. So it works over basically any field which with large characteristic 0 or bigger than 3. And this is also new. And because all previous IPS lower bound were over characteristic 0 or large characteristics. So the hard instance is the following. So basically it's a product of 2 by 2 matrices and 2 by 2 matrices. And the product of the determinant of 2 by 2 matrices. Right? So this is of degree n, but every Nunstein's refutation of this is going to be of the full degree of 2n. 2n is well, it's not full.
So the degree of the GI is that will be at least n, yes.
Where is G?
B.
Sorry.
It's G times Fi, right? That's how you count the degree.
Yeah.
So the degree of GI will be at least. The total
Correct. The degree of GI is going to be n, and the degree of this is going to be also.
And the previous result, the degree of the GI can be like n minus d. Something.
Yes, but this is also not full because the number of variables is bigger. It's still a lower bound. Now this is a lower bound. Yeah, this is the degree, and it works because of some. So the symmetry is here. So invariant here. Yeah, you can show that this is invariant under some action. Invariant is, you can think about it as partial symmetries. So it's not fully symmetric, but because it's partially symmetric, we can still exploit this and show this degree lower bound. Now I'm going to show you, and this also works over finite fields. And as I said, this was new because it was open how to do this kind of lower bounds over finite field. And also it's not a subset sum or subsum variant. So here is the summary of results. Lifting. Yeah. So what is a lifting? Now we want to take this notion of new notions of degree lower bounds and turn them into size lower bounds on IPS. So this, what is a lifting? For us, it will be just this. We start from F, hard for notions at degree. We plug in some gadget or function G with some variables. Usually disjoint variables Y here. And just run Y as a shortcut. And I plug in this and it becomes hard for CIPS. CIPS is IPS with C is some circuit class, constant depth, for instance. Actually, it should be Lin also. Never mind.
You mean that variables Y, they're still different?
They should be disjoint here.
Y1, Y2.
Yes, yes, yes. Maybe I should write in one.
This is like the 1 bit index gadget.
It's not a, it's a very abstract
shared
variable. It's not shared. It should have been y1, y2. I just was I didn't write it. It's just a conceptual diagram to explain what is lifting, which is just a substitution of the variable with other a function polynomial of other variables. Doesn't matter. I will show you what it is. Here it is, the actual lifting. Actually, it is also kind of simplified. So here are the results. So base instance is symmetric, fully symmetric. If we lift it with this, so let's assume wi, the variables, they were x before, and now I change it to some kind of simple gadget, zi, j, xi, xj. I have to extend also the number of variables to n choose 2. And it becomes hard for IPS thing where it is written as read once ABPs over large characteristics. So it becomes exponential. This generalizes FSTW21. Sorry, how do you choose J?
No,
Sorry?
he said it's I on the left hand side and I on the right hand side don't have anything to do with each other.
There you go. Okay, sorry, I don't get into I have only 25 points. So yeah, they don't. It's just okay, kind of. Sure. So So for the invariant, we do the same with the same lift. You get read once ABP, lower bound exponential, and also this matches the RAS and RAS-UDI of lower bound of n to the log n in the placeholder model multilinear formula IPS. So this works also for the multilinear formula, and this is over any characteristic bigger than 4 or 0. Yeah, the context here I wrote is FSTW, and also Andrews and Forbes had a nice lower bound in this model of constant depth IPS in the placeholder model. Now, if we take this basic vanilla subset sum and we do some complicated lifting, this is a simple lifting with just 4, 5 variables, but we have to do more. As I said, it's very technical. We can show that the following. So we have a constant depth IPS of log n individual degree. Refutation is some polynomial. It has individual degree and it is computed by constant depth formulas, IPS. Over here we need the large characteristic. Then we get a lower bound, which is super polynomial. Once polynomial, this improves my work with Iddo Tzameret and Thomas here. And it's based on, of course, all these based on this breakthrough by Limaya, Srinivasan, and Pandanath, the constant depth circuit lower bound for algebraic circuits. And this also exploits this new result by Garg, Amiredi, Kayal, Saha, Garg, and Fanake. Sorry, Amiredi should be here. There was some improvement for the proof about there, and we use this. Now, what is going on here? Circuit complexity. Yeah, we have also some circuit new functional lower bound there. That's not good. Now,
can you explain just again? I got confused about these J's. Are you somehow summing over the J's? Because otherwise it's hard to see why this multiple indexing, what does it mean? Like when you WI, you replace it by ZI.
it's not the same I. If I have XI, X1, yeah, you have to do something. You have to extend the number of variables, Xn, then you have to extend it to some n is n, and then you have to do all possibilities. So basically, it's going to be I, J, K, L, and Z. Well, the instance itself is going to be this.
It's like Einstein.
So Z, I, J, K, L, X, I, X, J, X, J, X, L. So this I call a lift of the subset sum, which is just Xi. So I just replace it. That's not, yeah, okay, let's see. We have 5 minutes. What do you want to see? The barrier or what is lifting? How is lifting used here?
Yes, it's a large characteristic. Is this just large constant or is it dependent on there?
No, depends on it.
And how bad or what is it? Or just
Oh, it's quite bad. Usually it should be 0, characteristic 0. Yeah, okay. Might be exponentially. Yes. Yeah, what do you want to see? Lifting, what is lifting or what is barrier? There's going to be a dichotomy. Okay, the barrier, I'll explain it. What is a barrier? We cannot use this with CNFs. You cannot use this method to prove any CNF lower bound. Let me show. Okay, I think lifting is slightly more intricate. This is the main idea behind lifting in IPS. Okay, the goal is this. We want to know about C circuit G, a C circuit or a circuit from class C that computes G such that what we know about G is the following. G is basically the IPS refutation. G times F equals 1 over the Boolean cube. And we want to lower bounds. Remember, in the functional lower bound, we have only single axiom. So we know that this is true. This is the refutation, modulo the Boolean axioms. And we want to use, because we want to lift the degree lower bound, so we want to use the Nullstandard's degree lower bound, which is usually linear. So how can we use it to get size lower bound? So I tell you the following in blue. The size of a polynomial P with 2 sets of variables, x and y, let's say they are n each, is in a lot of circuit classes of interest in algebraic circuit complexity, this size is lower bounded by the dimension of the following vector space. It's called a Val dimension. So you take P, the polynomial, with x, and then the y variables, you just substitute all possible beta signs, the n signs, right? Now you take this space of polynomials, it's a vector space, and it has dimension. If the dimension is big, then you get size, which is big. So that's one thing that is known from this. And it's, yeah, actually for the constant depth, it's not precisely this. It was before in our previous work, but this work it's changed a bit because we have to accommodate to the new result. Now, what is the lift? The lift here, well, I hope maybe here I also made some slight abbreviation which are not very accurate. So I take F and I lift it by changing the variables. Here I just wrote it like H, right? So H, X, Y is now the lift applied to each variable. So now we have 2 sets of variables, X and Y. Maybe I also increase the number of variables to make it happen like this. So let G prime XY be such that G prime XY times F after the lift is equal 1 over the Boolean cube, right? So I just lift and I consider the same strategy, the same refutation. So the refutation of the instance after the lift. So it's now G prime. It has both X and Y. So what I need to do to prove the size lower bound now is to show that the dimension of G prime, when I assign all the S's, all the bit strings, now I change it to M, it's not important. Because I didn't specify what is Y, what is the size of Y. Right, so I need to lower bound this dimension. Now, let's assume without loss of generality that G prime is multilinear. So if it's multilinear, I can assume this because it's a linear operator, so it just decreases the dimension. So if I get lower bound, it's okay. Now, the argument is this. The dimension of space of a polynomial is lower bounded. This is known by the number of distinct leading monomials. It's easy. Now, leading monomials in monomial ordering. We have some monomial ordering. the number of distinct leading monomials is lower bound on the dimension of the space. So we need to, that's the trick, we need to isolate distinct leading monomials in this space using this lifting. So what we do is this, that's a canonical example. So assume that G prime and then X, and this is one, the indicator ones for the choice of S is equal. So that's the trick of the lifting. The lifting should be such that G prime, the proof, when I substitute the Y's in with ones, it collapses to the original G. The original G before the lifting.
So this is just saying basically you're applying G to the G prime is applying, you're applying to like the inner product, basically? Yeah.
Inner product.
No, sorry, forget,
No.
no, sorry.
It's just an assignment.
Yeah, sorry.
And it collapses when you assign the Y's, it collapses to the original G in the
Yes,
X's.
just, yeah.
Now you have Nussstein's degree lower bound on this. So you know the degree lower bound. Now, what is the degree lower bound? So it collapses to X choices only of these variables. So now for different S, different set of choices of the variables, because the degree is high, I will know more or less what is the leading monomial. Because for different S's, yes, the degree here is going to be linear in the size of S. So for different S's, they will be very, very different in big enough in the variables, right? So I will have a lot of pairs that are distinct, and I will know what is I will have a lot of distinct pairs of leading monomials, and hence I will lower bound the dimension of the space, and hence lower bound the size of G, and hence lower bound the IPS refutation. This is kind of simple. Sometimes it's simple, sometimes it's very hard to do to get this. And we did this in our case. And the barrier is this. I think I have, sorry. Barrier is, this is the theorem, and thank you very much.
What was that second to last slide?
My question, that was gonna be my question.
This,
Yeah, no, just go to that slide.
Yeah.
No, not that one, which is the proof of this, yeah.
this,
No, forward,
This report.
forward, one more, that slide, yeah.
that slide. Oh, you see, no, this is the proof of the barrier. It's why you are interested by my handwriting.
Yes, no, but it's the proof of the barrier. What's the big idea?
Oh, the big idea is this. It's yes, the barrier in 2 sentences. Let's see if I can make it. Sufficiently strong proof system that has the barrier. Sufficiently strong means that if you have from Fi's that you know in the proof system, you can derive the end of them. Semicolon, it's still the same sentence. What is going to happen is because we can derive the end, if it's a Boolean, then the end of them is just basically lives in the ideal generated by the Boolean axioms. So it can always have a refutation in the Boolean axioms. So it might be a big refutation in the Boolean axioms, but then you can never have the product G, which is the product of the non-Boolean axiom, big. It always can be small. Hopefully that's explained this. Yeah. Any other questions?
Yeah, so I guess symmetric polynomials on the cube, right? They're just functions of the sum of the variables. Right? Because something that is symmetric on the cube, right? It only depends on the sum of the variables, right? So I'm wondering, it should be possible to get like this result by just thinking of like univariate problem, because essentially you have a univariate problem, right? Everything is univariate in the sum of the xi's. And I think maybe, I didn't have enough time to think this through, that maybe you can just do it in kind of some sort of a univariate polynomial result. You're really secretly talking about univariate polynomials.
Well, yes, maybe for the technicality, it might be helpful, yes. Well, let's discuss it offline.
Okay.
Thank you. Any-
Well, we haven't thanked, you know.